Hi everyone, my name is Faiza and I'm from UC Santa Cruz. Today I'm excited to present our work on content-inducing approaches to interactive story generation. This is a joint work with Alex and Snigdha. So automatically generating narratives is a standing and challenging AI problem that is different from general text generation or dialogue generation in that it requires composing creative and causally related sequence of events about a topic, which has local and global coherence and also thematic consistency. So the ability of computer systems to generate stories can be effectively used to generate various types of text, such as novel and news articles or movie scripts. And in particular, this field of research can be used in addressing the literary needs of learners with disabilities and enabling children to explore creative writing at early age by crafting their own stories and also as collaborative authorship. Um, Existing state-of-the-art models for story generation actually generate a story in a one go with limited initial inputs from a user. However, when human writes, they incrementally edit and refine the text they produce. And motivated by this, we want to explore the problem of interactive story generation, where a user provides cue phrases to guide the model generation. So let's see what is the task. So this here we are showing the scenario where given a prompt such as John walked into the kitchen, the system generate the story one sentence at a time, and the user gives the content of the next sentence using some cue phrases. So for example, given dark, the system generated was dark and cold. Given light switch, the system generated he turned on the light switch, and so on and so forth. And we want to note that the generated sentences need to fit the context and also be semantically related to the provided cue phrase. So the problem formulation would be that given a generated context so far, noted as X, which is a sequence of tokens, and also cue phrase for the next sentence, denoted as C, our model generate tokens of the next sentence of the story, denoted as Y as a sequence of tokens. And also we let the definition of cue phrases open-ended so as to enable flexibility in user interaction. However, they are typically one or two words in our case. And so when generating the end sentence, the model takes all n minus one sentence as a context along with the cue phrase. So next we want to introduce our model architecture, basically the content-inducing decoders. So I describe two novel content-inducing approaches for incorporating external knowledge, that is cue phrases, and we call them cued writer and relevance cued writer. So the models share an overall encoder-decoder architecture shown here, and the two proposed models use the same encoding mechanism and only differ in their decoders. So what we did is we adopted dual encoding approach where two separate but identically similar encoders are used to encode the context, called context encoder, represented in the green box, and also cue phrase called cue encoder, represented in the purple box. So we see that we use the same encoding mechanism, and we have dual encoder. So each encoder layer contains architecturally identical encoder blocks and with unique trainable parameters. So obtaining individual input vectors from context and cue, new representation are constructed through layers of encoder blocks for both context and cue. So going to our main contribution, which is content-inducing decoders, and our first model called cued writer. So the main intuition behind our first model is that since cue phrases indicate users' expectation of what they want to see in the next sentence of the story, they should be used by the model at the time of generation, that is in the decoder. So we describe how the cued writer decoder work in this slide. So after processing the two types of input in the context and cue encoder, the model includes their final encoded representation, that is XL and CL, shown here, into the decoder. And again, the decoder consists of like L identical layer of decoder block, and we only show one layer as a representation. Focusing on the attention units in the block, which is in orange, each decoder block contains a multi-head unit, which is the standard self-attention measuring the intra-sentence agreement, and, and also an encoder-decoder multi-head, and also a Q multi-head units, which respectively let the decoder to focus in relevant parts of the context and Q phrase. Lastly, after we adopt a gating mechanism to integrate the semantic representation from both the decoder and the queued multi-head obtained from the previous step, and allow the model to flexibly learn how much each representation should contribute and pass the resulting output to the feed-forward neural network. So our second model, called relevance queued writer. So we know that in the decoder of our previous model described earlier, it captures the relatedness of the context and cue phrase to the generated sentence, but does not study the relevance of the cue phrase to the context. So what if the given cue is off topic or unrelated to the context? So we incorporate this relevance in the decoder of our next model, relevance queued writer. And like the decoder block is shown here, which is similar to that of the queued writer, except for two additional units. One is context queue and relevance multi-head units. The context queue multi-head unit is to characterize the relevance between the context and the cue phrase, so as to highlight the effect of the words in the cue phrase that are more relevant to the context, and thereby promoting topicality and fluency. And this relevance is then provided to the decoder using some relevance multi-head units. And finally, for both models, we have a linear transformation and softmax function, which is applied to convert the output produced by a stack of decoders to predict the next token probabilities. And the likelihood is used to minimize the cross-entropy loss. So going to our dataset and training details and some evaluation measures. So we use ROC Stories corpus for our experiment. It contains around 100,000 5-sentence long stories with a rich set of causal and temporal sequences of events. Since this dataset doesn't have the cue phrases as input, and also in order to scale our model training, we use a rake algorithm to automatically extract important phrases from the target sentence. And more statistics on the cue phrases are reported in the paper, so please check our paper. We use several baselines to evaluate our proposed model. Our first baseline is an LSTM-based sequence-to-sequence generator. And in order to incorporate user-provided cue phrases, we concatenate the context and the cue phrase with a delimiter token, separating them before passing it to the encoder. We also include a dynamic and a static model proposed by previous our story generation model, which we modified to work in our setting. Basically, we use the two variation dynamic, which generates the story one sentence at a time, which is a similar setting to ours, and the static variant, which gets all cue phrases at once and generate the entire story. Also, to verify the effectiveness of our content-inducing approach, we use a vanilla transformer as another baseline, which simply concatenate the cue phrases with the context. And so we have two sets of evaluation, both automatic and human evaluation. For automatic evaluation, following credible work, we use perplexity and blue scores to evaluate different models. Lower perplexity is better, showing like higher fluency. And also we use blue score 1, 2, 3, blue 1, 2, 3. Also, to evaluate how well the story generation model incorporates the cues, we use an embedding-based score, gradient matching, that measures the relatedness of the generated story with provided cues by gradually matching them with each token in the story based on the cosine similarity of their word embeddings. And finally, since neural models has been shown to usually suffer from repetition issues, we additionally evaluate models uh, using several metrics which measures the repetition amount for which lower scores are better. For example, we use repetition 4, which measures the percentage of generated stories that repeat at least one foreground. And and also we have a different level of human evaluation, which I will explain in the respective slide. So going to our empirical results. So first of all, we see that both of our proposed model outperforms the dynamic and static. We also have additive gain from modeling the relevance in our second model. Also, stories are more related to the cue phrases from our proposed model. And also finally, the proposed model significantly outperforms all baseline with respect to the repetition scores. We also have another repetition measurement, which is called inter and intra story repetition scores, which are depicted in these two plots. The two last bars, which are our proposed model, they are actually almost comparable, but they show a general superior performance compared to other models. And finally, since automatic metrics cannot evaluate all aspects of open-ended text generation, we also conduct two different human evaluations, and also there are more in the paper, so please check out. So we make a pairwise comparison where both models are provided the same prompt and set of cue phrases, which are randomly sampled, and three judges evaluate 100 pairs of stories. This figure shows the percentage of preference for our stronger model, relevance cued writer, over the baseline. So we see that judges prefer our model over our other baselines. So we also conduct a more fine-grained sentence level evaluation where we provide an incomplete story passage and just a single cue phrase to the two model to generate the next sentence. And we ask the judges to choose which of the two sentences actually better based on their fluency and semantic relevance to, first of all, the input, which is an incomplete story, and second of all, to the cue phrases. So we see that here in the lower plot, we see that model, the relevance cued writer model was preferred over seek-to-seek and vanilla in 72% and 64% of the cases, respectively. And also comparing the two proposed model, we again see additive gain by modeling relevance in the cue, and by actually modeling cue context relevance. We also provide a thorough qualitative results, giving insight on particular errors different model make. So for details on these qualitative results, please check out our paper. And finally, as a summary, what we did is we explored the problem of interactive storytelling, which leverage human and computer collaboration for creative language generation. We proposed two content-inducing approaches to incorporate additional information into the generation phase. We evaluate the utility of our approaches through several experiments and demonstrate that our model outperformed competitive baselines. And finally, we suggest other significant aspects of a story generation, such as modeling of discourse relations and representation of the key narrative elements, which could be possible future direction. And thank you so much for listening, and I'd be happy to take questions.